Bismillah ar-Rahman ar-Rahim. Welcome to the second part of this tutorial. In this tutorial, I'm going to describe the various kinds of attacks that exist on ML and deep neural network models. So before we get started, let me just give you some brief description of the canonical supervised learning task of classification and how it works. And we will use that to then see how an attacker can use the same algorithm to attack the ML model. So here we see that we have a deep neural network in which we have an input layer in which the image is vectorized and provided as an input to the deep neural network. The input layer has M components or M neurons, and then you have multiple hidden layers that apply transformations, nonlinear transformations. They make use of activation functions like ReLU or sigmoid, and then eventually the data is passed to the second last layer, which has N components. And in this case, we consider that we're interested in classifying the image into N possible classes. And then it is typical to apply softmax to produce a probability distribution at the last layer. And the last layer also has N number of components. So like we see here that the output of the softmax layer, when all of that is added up, you get it equal to 1, which is the definition of a probability distribution. So let's see how a classifier works. So when you have images from a particular class, all of those are given to the input, and we expect that the neural network will learn the mapping of the input to the correct label. In this case, the correct label should be the first item should be 1, which corresponds to the class of a cat. In the case of another category, the second item in the last layer should be set equal to 1. And similarly for mug, which is in this case the second last entry, and finally a dog, which is the last entry, should be 1. So we want to learn a mapping in which if we are given an input image, we are able to describe which class it belongs to. So in optimization, the true goal is in fact to minimize with respect to theta, which is the deep neural network model parameters, the population risk. Basically what this risk is measuring is the loss, which is the difference between what the model is saying and what the true labels are. So we would see this discrepancy and we want to minimize it in expectation, which is probabilistically for all the possible values in the distribution, we want to minimize it. But since we do not know the probability distribution, we have to do our working on the data that we have. So for that, we make use of empirical risk minimization, in which we just sum up the loss or the difference or the discrepancy with what we have and with what the real labels are. And when we say that we're training the model, we're in fact changing the parameters so that this loss is minimized. And we have many different optimization algorithms for incrementally and iteratively minimizing this loss. So we see here a 3D image in which we have two parameters of the deep neural network, theta 0 and theta 1, and we have the loss function. And in fact what we're looking for is we are trying to find our way to the bottom pit, the value or the values of the DNN model parameters that minimize the loss function. So typical method used for this is gradient descent method, and the reason is that these loss functions are typically non-convex, and for these kinds of loss functions we cannot make use of exact methods. Those will be applicable for convex optimization techniques, but that requires the loss function to be a helpful convex type. But in this case, because this is non-convex, we make use of gradient descent, which is a very simple algorithm, but it does not give us any guarantees that we will find the optimal. So it basically gives us a locally optimal value. So let me now give you a brief tutorial on how the weights of a deep neural network are tuned. So for example, if a banana image is provided to the deep neural network, initially the weights of the model are not tuned. So we would expect to not get the right answer. So we see here that the probabilities are all over the place, and the highest probability matches to that of the item dog, but this is in fact not the case here. So we will calculate the loss would be rather high here, and we would then evolve or change our model parameters so as to reduce the loss. So the loss is calculated by comparing the real answer, which in this case would be just banana would be 1, and all of the other classes would have the value of 0, and we compare it with the probability distribution that we have, and we compute the distance between these. It is typical to use cross entropy, and we can represent that as in this case a loss function over the parameters w. In this case, w is the weights of the deep neural network, and it is the weights that we are changing in an attempt to decrease this loss function. So we can represent this as the Jacobian, which in fact tells us which way should we change the weight so as to reduce the loss function. Remember, in the usual course of events, we want to reduce the loss or the difference between the true classes and the classes that we have. And for this, we actually make use of the gradient, and we make increments in the direction opposite to that of the gradient. This is because gradient points towards the direction of the steepest ascent, which is if you want to maximize, you go in the direction of the gradient, but if you want to minimize, you go in the opposite direction. So we change the weights according to the formula that is shown on the left hand side of the screen, and in this way we back propagate the differences and we change the weight parameters. So this is known as the training of a deep neural network. In fact, what we are doing is that we are tweaking the model parameters so that the cross entropy loss reduces. When we are crafting an adversarial example, we are going to use the exact same algorithm, but now we just change the objective. So instead of minimizing the loss with respect to the weight, we in fact maximize the loss with respect to the input. So now we're interested in seeing that, okay, we want to maximize the distance between the true class and the classes that we have, and for doing that, what we can do is we can change the pixels here. So this is known as gradient ascent with respect to the image, and this is a very simple algorithm, and it's very simply illustrated here that we are just now changing the input image rather than the weights, and the rest of the training algorithm is the same. So with this, we can change the input in ways that would maximize the loss, and when we're able to do that, we call that an adversarial example. So the question arises, I hope you would already be guessing the answer to this. I've just shown that why is adversarial ML attacks so easy to craft, and like I've mentioned, they are easy to the attacks are easy to be launched, or we can find the adversarial example so easily just because we are making use of the same algorithm. So because deep neural networks are typically easy to train, it's also easy to create adversarial examples for that. These deep neural networks typically make use of differentiable functions, and they make use of gradients to navigate the loss function. We are still navigating the loss function, but now instead of minimizing, we are maximizing the loss. And also, we are not changing the weights of the parameter. We will keep the parameters as they are. We will just be changing the input image, the pixels of the image. So let me show you an example of this. So we are giving an example of a bird to a machine learning model. The machine learning model parameters are trained so as to minimize loss, so it will correctly figure this out as a bird. If we are interested in maximizing the loss with gradient ascent to create an adversarial example, we will modify the input. And we will ask the question, okay, what happens if I nudge this pixel in a certain way? And we ask this question for every pixel. And then we change the pixel in ways that will maximize the loss. And when we have done that, we have an adversarial example for which we shall see that when that image is given to the machine learning model, we get an incorrect answer. So to illustrate this, we make use of the very simple, the fast gradient sign method, which is one of the earlier attacks. In this, we start with the machine learning model. We do not change its weight, but then we start thinking about how do we change the input image so as to maximize the loss. And for that, we make use of the gradient of the loss function with respect to the input. So I emphasize again, this is with respect to the input. So we find the way we can change the input to maximize the loss. Here simply we take the sign of it and we multiply it with epsilon. So in other words, with FGSM, it's just a simple one-step procedure, and that is why it's called a fast gradient sign method. We just change every pixel either by plus epsilon or minus epsilon according to the gradient. And when we've done that, typically it is seen that this attack, although it's very simple, it's very quick, still it is able to defeat the machine learning model and make an error in many cases. So the input is shown on the left hand side, the top left hand side, and on the bottom left hand side we see the addition that is made. So this is magnified just to be something that we can see on the screen. We see that this is very simple noise. When this is added to the image is classified incorrectly by the machine learning model. So for the perturbation, we see that its L infinity norm is epsilon. So just to refresh, I would like to just state that the L infinity norm is the maximum entry in a particular vector or a matrix. So what this means is that in this matrix, the highest perturbation is just epsilon, which is chosen to be a small value. When the input and the perturbation is added, then we see that the machine learning model is misclassifying the image, which is the purpose of the FGSM attack. So let us now talk about the attacks. We can create a taxonomy of attacks according to various features related to the attacker or the intent of the attacker. We can classify according to the adversary's knowledge, according to the goal of the adversary, the capability, the specificity of the attack, what is the attack exactly trying to do. We can also specify on the bound of the perturbation. Some perturbations give a bound on the maximum change then can be made. Some of the perturbations bound on the number of pixels that can be changed, and so on. And also we can classify according to the perturbation seeking algorithm. So let's start by talking about the adversary's goal. An adversary's goal could be simply to attack the machine learning model's integrity. That is, the answer the machine learning model is giving should be made incorrect. So you're interested, if it's a classifier, you would be interested in increasing the misclassifications. You may also be interested in compromising the availability of the machine learning model so that it's not available when it is required. So this is akin to the denial of service attack. You may also be interested in, an adversary may also be interested in attacking the confidentiality or the privacy of the data, which is the attacker may be interested in knowing the machine learning model, the parameters used, or even getting access to the training data. And because this is confidential, you don't want this to be made available. The adversary's goal can be stated to be attacking the confidentiality of the system. So if we compare attacking integrity versus confidentiality and privacy, breaking integrity in the context of adversarial machine learning would mean model evasion. So the kinds of attacks we have just seen are known as model evasion, and they are launched at the time of the testing. So we don't mess with the training phase. In this case, the training is done independently, but now you are interested in attacking the system at test time. In many cases, you can assume that the model parameters are known and you want to create an adversarial example based on that knowledge. The kind of attack at test time is known as, in modern literature, it is known as model evasion or adversarial example. You may also be launching other attacks which gives incorrect results to some or all users. Whenever your attack is focusing on creating or getting incorrect results, you are basically attacking the integrity of the system. You may also, as an adversary, be interested in breaking the confidentiality or the privacy. And the interest here is to infer sensitive information about the training data, about the evaluation data, about the learned model. In many cases, these informations are private, and the model, the owners of the model do not want this data to be shared. So if an attacker wants to recover this, this would be an attack on the confidentiality or the privacy. We can also differentiate attacks according to how much knowledge they have of the ML model. So in a white box attacker, the machine learning model is like a white box that you can see through. You can see the model being used, you can see the optimization algorithm being used, you can see the weights being used, and so on. So in a sense, a white box attacker knows the model and all parameters. In contrast with a black box attacker, you do not know what the insides of the machine learning model is. Typically, you just know what you can query the system. You can ask it a question, you can give it an example and see how it responds. So a black box attacker is different from a white box attacker in the kind of information it has about the ML model. So another way of classifying the attacks could be to differentiate between targeted attacks and untargeted attacks. In an untargeted attack, you just want the machine learning classifier to make an error. So you want it to say something that it should not really be saying. But with a targeted attack, your interest is to get the perturbed image X dash in this case to be classified as some target class, T in this case. So you are perturbing the input image or the input signal in some way, but then you're also interested in making it, the machine learning model misclassify it in a particular way. So One very important aspect of adversarial ML security is to talk about the threat models. So here we see an insightful quote from Sun Tzu, the classic Chinese war general. He says that if you know the enemy and you know yourself, you need not fear the result of 100 battles. Similarly, when dealing with security of adversarial ML models, we need to know about our adversary and we need to make our assumptions explicit. So, for example, let's see a taxonomy of the various kinds of threat models. We should be stating, when we are, for example, proposing a defense, we should be stating what kind of an adversary are we assuming. It is your defense can only be verified and stated to be good or bad in respect and with the knowledge of your threat model. So with adversarial knowledge, you may assume a white box attack, a black box attack, or somewhere in between, in which you have some information but not all of the information. You may also be specifying the adversary's specificity, whether the adversary is interested in getting a targeted misclassification or just a random misclassification. And also, what is the ML attack surface? How is the data being collected and processed? What is the model? What are the decisions? What does the adversary know about these things? Also, the attack frequency. Is the attack just a single time attack or is it an iterative attack? So it's common for the iterative attacks to be more powerful because they can continuously improve their attack strategy. But with just a single time attacker, these attacks are constrained. They whatever they have to do, they only have one chance. Adversarial falsification, what kind of a misclassification is the adversary interested in? Does the adversary want a false negative or a false positive? So all these things are stated and then studied for both the attack and the defense. So let me just illustrate the various adversarial goals and demonstrate which one is easy and which one is not. So we have listed 4 different adversarial goals and we have classified them and gradually we see that the first attack is easy, confidence reduction is easy, misclassification is harder than that, targeted misclassification is typically even harder than that, and source target misclassification is hardest. Let me show you how this works. So for example, we see a bus here. It is correctly classified as a bus. The second label is that of a bus, but with confidence reduction, we're interested in just affecting the model so that the model is not as confident. So with this, we changed the probabilities of different classes and we were able to reduce the confidence of the real class. In a misclassification, we change the probability so much that the most probable class actually shifts. For example, in the probability vector on the bottom of the slide, we see that now the class 1 corresponding to a dog is now the most dominant class. This is a misclassification. With a targeted misclassification, we may start with random noise and we want to change it in ways that would perturb the image and make it into something, some targeted class. With a source target misclassification, you are given a source image and you make perturbations in a way that transforms the image into some specific class. We can also talk about the adversarial strength and the adversarial capabilities. So an adversary who has knowledge of the architecture of the model and the training data is a very empowered adversary and it can easily attack the ML model. It is harder to attack the ML model if you just know the architecture but you do not have the training data. And if you have only access to the training data, the attack is harder still. Sometimes you just have an access to an oracle. You don't have access to the ML model, the architecture, the training data, but you can just ask it a question and know the correct responses to different queries. So kind of a black box attack. And finally, you just have some samples. We also see on the right hand side, white box attacker are typically easier for the attacker, whereas the black box attacker assumes less, and it is black box attacker is a more difficult assumption. So in when you're attacking, we typically make lesser assumptions about the knowledge and we assume a black box attack. And if you're able to demonstrate an attack in this setting, the attack is considered to be more powerful. But when you are proposing a defense, then it is common to assume an adversary that is a white box attacker, because then you are able to show that your defense works well even in the case your adversary is a powerful one. So just some history of the attack types. The first attack was shown in the work of Segad. This was the LBFGS algorithm. They showed through a line search method that adversarial attacks are possible, but their attack was not as simple, and therefore it took some time. The latter attackers actually worked on this and proposed a very simple algorithm like the FGSM, which was an attack that was able to create an adversarial example in very little time. And then other examples continue to be proposed, and some of them are listed on the slide. We will consider a few of them, but before talking about them, let me talk about the perturbation measures. Perturbation measures are how do you define what kind of a change you are able to make in an image. For example, if you totally change an image, then you would expect the machine learning classifier and even humans to classify differently. In adversarial example, we are interested in changing the image in ways that are imperceptible to human beings. So the perturbations are very small. So let's talk about the distance measures that are used to bound the perturbation. In an L2 norm attack, you aim to minimize the squared error between the adversarial and original image. And these typically result in very small amount of noise added to many different pixels. And overall, no single perturbation is high. So these are the L2 norm attacks. These are measured. They measure the Euclidean distance between the adversarial example and the original sample. In contrast, in an L infinity norm attack, you are interested in bounding the maximum change that you can make. So when you are given a vector or a matrix, the L infinity norm gives you the maximum value. So in these attacks, the maximum change that you can make is bounded. So L infinity denotes the maximum change for all pixels in adversarial examples. This constraint forces to only make very small changes to each pixel because you have bounded the maximum that is possible. Finally, in an L0 norm attack, it basically focuses on the number of modified pixels in the image. So just as a reminder, the L0 norm of a vector tells us the number of non-zero entries in it. In a similar fashion with the L0 norm attack, we are focused on the number of pixels we are going to change. So if the L0 norm is bounded, it means that this is the maximum number of pixels that you can change. So in such an attack, we force the attacker to modify only very few pixels. So I'll show you examples of this, but before going into the details, like I've mentioned before, not all perturbations are adversarial. Typically, we call an example adversarial if it will fool the human because it is imperceptible. But let me say this again. So with an adversarial example, we want to change the image in imperceptible ways that will not be detected by humans, but which will fool the ML classifier. So we see here some example perturbations. The clean example is shown on the left hand side. And we see the image in the middle is perturbed, but it is not perturbed in a very specific way. So it's difficult to see what the of what this digit is, but when it is corrupted in a specific way, it changes the class. So we are interested in stopping this from happening. With a random perturbation, it's not necessary that your class will be flipped. It is also possible for perturbation to change an input to some rubbish class that does not exist. So the take-home message from this slide is that not all perturbations are adversarial and they are not as effective. We are interested in creating as an adversary the right adversarial example that can fool the ML classifier. So how attacks are formulated? So the attacks are formulated in the way that is described here. We want to cause a misclassification with minimum perturbation. So the image X is changed with delta X, and we want to change this delta to be small, but we also want that this delta is sufficient to change the label of the image. So in this optimization problem, we are finding the minimum delta that is able to flip the class of the input. With a targeted misclassification, the only difference here is in the first optimization, we were just interested in it being inaccurate, in getting it to misclassify. But in the second optimization, we are interested in getting it to misclassify in a targeted sense. So these optimizations are typically intractable. They are non-linear, non-convex, which means that typical convex optimization techniques cannot be used. But again, there are some heuristics and some methods that have been adopted for such methods, which we will be using. So that will be discussed shortly. So the problem here is that we are interested in maximizing the loss by adding some perturbation, and we want this perturbation to increase the distance between the true value and what will be resulting from this. So we see on the left hand side that the loss landscape or the loss function is not convex here. So what are the options that are available? So the first option that is available is just to do a local search. Because we are doing a maximization here, any feasible solution would be a lower bound. And we can try to improve upon this, but this will not result in an optimal solution, but it may result in a good enough solution. The other approach we can do is we can try combinatorial optimization. This will exactly solve the objective, but this will not be possible except on very small data sets. So for data sets like MNIST or similar data sets, it might be possible with a lot of computational resources, but such solutions are not possible for large problems. Finally, some people have proposed convex relaxations, and with this you can get an upper bound on the maximization that you can achieve. Special cases of this can be solved leveraging insights from robust optimization, which is a field which has emerged from robust statistics. There's a lot of work there, and people have used these insights for adversarial ML in the last 3-4 years. So this is an example of a local gradient-based search method. We can use an approximate solution using gradient-based methods. We know that in gradient-based optimization algorithms, we can easily find the solution, but they are not guaranteed to be optimal. It's common to use gradient-based methods for crafting adversarial examples, and we will just see 3 of these. The first one we shall see is LBFGS, which was the first one, and then FGSM was proposed, which is a very simple method, and then there is the JSMA method, which is another gradient-based method, but it uses a different L norm. So the first attack that was launched was in the first paper by Segad, which in fact showed that these neural networks are prone to these attacks. And they were the first researchers to show that perturbations indistinguishable from human observers were sufficient to force deep neural network model to misclassify an image. And the optimization they used was as shown. So they are interested in adding some perturbation, which is shown as R here. When that is added to the image and passed to the deep neural network, you want the image to be changed from its original label. And while doing this, your objective is to minimize the 2 norm of the perturbation that you are adding. So this was able to achieve success, but the method was computationally complex. The next work which optimized this was the work of Carlini, which revisited the LBFGS method and used the Adam optimizer to produce an answer, an adversarial example, in a more efficient fashion. But comparatively, when we compare to the other approaches, these works based on BFGS were still computationally complex. They were also iterative methods, so they would keep on going until they produced the answer. So one can reduce this cost by compromising the attack's effectiveness. So when we will see the FGSM method, the FGSM method is not an iterative method, it is just a one-step method, which is typically effective, but its main forte, the main selling point of FGSM is that it is very fast, it is very simple. Similarly, if you want to make LBFGS more efficient, you can simply run it for fewer iterations. It will give you a less expensive attack, but it will probably also have a lower success rate. Let me now talk of the FGSM method. In an FGSM method, as mentioned before, you have an image in which you add certain perturbation. That perturbation is calculated very simply. It is computed using the gradient of the loss function with respect to the input, and you just change the input pixels with either an epsilon or a minus epsilon in the direction of the gradient. So with this, the attack is very simple. The difference between this and the earlier attack is that now we are bounding the L infinity norm of the perturbation that we can make. So the L infinity norm of R here is equal to epsilon. That is also shown here, that this L infinity constraint, it limits the maximum change for all pixels in adversarial examples. So let me show you how this works. So if we are given this original image with an FGSM, if the adversary power epsilon is 0.1, this is what you can produce. And if you have a higher power, an epsilon of 0.2, then the attack is going to produce an image like this, and so on for different kinds of adversary power. Typically, we force the epsilon to be a small value because we want the change to be imperceptible. But the important point to remember here is that with FGSM, the constraint we are placing on the perturbation is an L infinity constraint. Let me now show you another attack which has a different constraint. In this, you have an L0 constraint. In other words, you are limiting the number of pixels that can differ between the input example and the adversarial example. So let's see in this case how the attack will create adversarial examples. So the originals are shown. These are digits 0 till 9 from the MNES database. And with JSMA, you can see that you can change the image. In this case, you are not uniformly changing many pixels. You are just changing the least number of pixels. When you have that constraint, for example, if the adversary strength is 0.1, the maximum number of pixels that you can modify is 10%. And that is the only constraint that you have. You can actually change the pixels by a relatively high value, but you're only limited to just 10% of the pixels. So here we see that with this, we are able to produce attacks that are also quite powerful. GSMA can be used to launch an targeted attack. So in this case, we have an iterative approach for a source target misclassification. With the L0 constraint, we are able to see that almost any arbitrary input class can be changed to any arbitrary output class, and GSMA is able to do that using a gradient-based method. Finally, I will talk very briefly of another method which makes use of convex optimization techniques. In this case, you make use of gradient descent, but also you project it back to the region, the feasible set. So for example, if you are starting you go outside the feasible set, then you project it back to delta, which is represented here by the feasible set. So you have an iterative method that continuously projects you back to the feasible set, which ensures that you're regularly making progress. And with this projected gradient descent method, the authors Medri et al. Have shown that they're able to create relatively powerful attacks. So let me now conclude this presentation on the taxonomy of attacks on machine learning and deep neural network models. We saw that all components of machine learning pipeline are vulnerable to attack. We also saw that the attacks on ML models can be divided on many fronts. So we can divide according to the knowledge of the adversary. The adversary may be white box or black box. We can also classify according to the perturbation capability. We may constrain the L0. We may have a L0 constraint or an L2 constraint or an infinity constraint. We may also have different kinds of attacks according to the time of the attack. Is the attack on the training data, or is it at the time of the training, or is it at the time of testing? And finally, we can classify the attacks according to which attribute of the security is attacked. Is it the integrity, reliability, confidentiality, or so on? So with this, I come to the end of part 2. Inshallah, I'll see you in the next part.